don't mind opening to chapter 27. Chapter 27 starts with this excerpt by Schoenberg, and so we're getting into the realm of atonal theory. And I always kind of give an intro to atonal theory, and I say, hey, everybody, get rid of this idea of a tonic pitch. Because when we say atonal, really we mean without tonic. And atonal music really aims at getting rid of a central pitch, getting rid of this idea of diatonic scales, diatonic modes, and really going for an equalization of all 12 chromatic pitches. So not one is the central pitch, right? And this is where dodecaphonic music or 12-tone music comes from. This idea of 12-tone music is, hey, no more tonic pitch, no more revolving, no more hierarchy, no dominant chord, no predominant chord, no triads. We're getting rid of all of this, right? We want to equalize everything, right? Because music has developed to this degree. We've done everything we can with tonal music, and now we're going to banish it, essentially. So atonal music really is music without a tonal center. And so when you're looking at modal music, when you're looking at music that uses the particular synthetic scales that we were looking at last semester, really we would describe those, I don't know if we would describe them as tonal because they don't really fit in our tertian harmonies. They do often have a central pitch around them. So I don't know that we would describe it as atonal music specifically. Okay, so atonal music, because it sits outside of what we know in the tonal realm and it doesn't use tertian harmonies, theorists had to come up with a different method of analysis. And this different method of analysis is called set theory. We're going to get rid of letter names. We're going to get rid of any sort of triads, seventh chords, everything that we've done. Basically, we're going to say, we're not really going to use that right now. We're going to be using sort of some of the same ideas of collecting pitches, organizing them, finding relationships across a particular piece. But we're going to be doing it not with letter names and notes, like the note letter names, but rather we're going to be doing them with what we call pitch class integers. And really it's numbers. Okay, we're going to be manipulating those numbers. So let me just play for you real quick this excerpt out of a chapter, and I'm going to jump over to it in the book here. It's not showing me that chapter. There we go. I'm going to share my screen for you real quick. I can't see it yet. There it is. So you're going, that's a little out there, right? There's nothing really to hang on to. But more importantly, if we're looking at this as musicians, as theorists, how do you analyze this? How do you figure out what's going on? Obviously, the composer had something in mind. And we derive a little bit from that, of course, of some of these organizations. So we have to use a different approach, right? Okay. So let me then jump over to the worksheet, and I'll share this with you as well. I'll tell you what, I'll just share it with you with some of the answers to this. And I'm going to bounce back and forth between this and between my blank staff paper. So I talked about this idea of set theory. We're getting rid of tertian harmonies. We're getting rid of scales. We're getting rid of note names, all of that. So you're probably saying, well, gosh, aren't we using the same pitches? All we have is 12 pitches, right? And that's all we can deal with. Yes, we're going to use them, but we're just going to use a different labeling system. So the labeling system we're going to be using, of course, this is called set theory or atonal theory, and you'll understand why. In this theory, we're going to equalize all of our pitches through the octave and through enharmonic equivalence. Now, what does that mean? Well, let's go over here and let me get rid of this. So at the very beginning of theory, we talked about range numbers or octave numbers. Right? We said this was C4, and this is C5, and this is, excuse me, this is C6, and so on and so forth. We're not going to specify octaves anymore. Right? These are all just the same pitch. Okay? As well, this is what we would describe as octave equivalence, right? We won't discriminate between the different octaves. Okay, and then the other idea here is that we're not going to show differences between this and this, right? We would say E flat and D sharp. And this is important if we're operating in different key areas or different tonal centers, but we're not going to use that anymore. These are equal, yes? So set theory relies on this idea of octave equivalence and enharmonic equivalence. So let me give you a better example of this. So let's say you had this note right here, E flat, and then you had this note right here, and then you had this note way up here. I'm sorry. I want to give you a different note. This note right here. These are all the same note, right? E flat, D sharp, F double flat. So instead of saying E flat, D sharp, F double flat, these are all the same note. We're going to get rid of octave equivalence. We're going to get rid of enharmonic equivalence. And these pitches are all what we would describe as 3, right? This would be the pitch class integer we would use to describe this particular note. Yeah. Okay, so that sort of describes to you what enharmonic equivalence and octave equivalence are. Let me lay this out for you in a little bit of an easier way to see. And looking at your book, you should be able to see this too. So all of my notes starting at C, we're going to start at C. C is 0, pitch class integer 0. And we say PC or pitch class. And the reason we say pitch class is because when we say 0, that encapsulates all of the enharmonic equivalents of C, all of the octave equivalents of C. So 0 is B sharp, 0 is D double flat, 0 is any of those notes at any octave. So pitch class, meaning it's that entire set of letter names of octave equivalent notes, all combine into one single number, which is 0, or one single integer. That's this idea of pitch class. Okay, same idea here. D flat or C sharp, or whatever you want to call it. This will be 1. D is 2, and all the enharmonic equivalent and octave equivalent is 2. E flat is 3. E natural is 4, and again, E natural could also include F flat, which is also 4, all the same idea. F and all of its enharmonic equivalents and octave equivalents is 5. F sharp is 6. I'm going to zoom down here. G is 7. A flat, G sharp is 8. A natural, E double flat, G double sharp, all 9. B flat is 10. And often we will use lowercase t for 10 as shorthand because we'll be putting these pitch classes into sets. And sometimes we won't use commas. And so it's easier to see the difference between 1 and 0 versus 10 just to write a lowercase t. It's just kind of shorthand. and 11 or lowercase e and 11. So these are our pitch class integers. Integers? Am I spelling that right? I don't know. Yes, it's an E. I don't know why I second guess myself. Let me just stop real quick. Any questions so far? So again, we're moving away from notes, we're moving away from scales, we're moving away from any letter names, sharps, flats even, and we're just using pitch classes, pitch class integers, meaning we're assigning a number to a whole range of different notes, right? But they're really all the same note, okay? And these pitch class integers will always be the same, meaning C is always 0. C sharp, D flat, B double sharp, all the same note, is always 1. D is always 2. E flat's always 3. So these will always be the same. And that helps us with consistency as we're analyzing these different pieces. And of course, as you can imagine, we can start to gather these pitch classes into sets and to see how those sets are transpositionally related or inversionally related across a particular piece. Okay, so a lot of our theory hinges on this idea of pitch class integers, right? Where we have enharmonic equivalents and octave equivalents. I'll keep moving on. So as I said before, sorry, I forgot to share my screen. There we go. Takes a minute sometimes. Boom, there we go. As a result, we use the term pitch class or pitch classes to talk about a particular note pitch. And we just said this, right? The class of pitches, all the pitches that are enharmonically equivalent, octave equivalent. Right? And more specifically, we call them pitch class integers because we're using integers or numbers to describe them really specifically. Okay, so instead of using note names, flat sharp, set theory uses, like I said, and I'm going to abbreviate pitch class with PC, pitch class integers. C, B sharp equals 0, D flat, C sharp equals 1, You can keep going with this. So since we have 12 different pitches inside of our realm of our tuning, at least, or our realm of pitches, right? Some music has more using quarter tones and other things, but we just use half steps. And so we divide the octave, those relational pitches that are an octave apart, right, through frequency. We divide that span into 12 equal parts. And so we have 12 different pitches that we can choose from. And so for that reason, we use what we call mod 12. And the most analogous thing that we can use for mod 12 in music is that of the clock, right? So time is in mod 12. So often I refer to the clock as our reference in looking at or mapping or showing relationships across our pitches or across the spectrum of pitches that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, I'm going to use the lowercase t for 10. And I'm going to use a lowercase e for 11. I'm sorry if that's confusing. This is what I'm used to doing, so you'll just have to carry on with me on this. I have one question. Is atonal music the same as 12-tone rows or something? Yes. So we would say 12-tone music, or what we call dodecaphonic music, which is a very particular technique, right, of atonal music, where we're organizing music into 12-tone rows, a predetermined 12-tone row, and then taking those rows and manipulating them through inversion, transposition, or retrograde. Yes, it is a type of atonal music. 12-tone music is probably the most it probably has the best label for atonal music because it really is trying to equal all 12 pitches and not have a tonic pitch. So yes, yes, definitely. It would fall under the umbrella of atonal music, if that helps. Or maybe you could even say it's the epitome of atonal music. Okay, so jumping back here to mod 12, we can see all of our pitches laid out here nicely on the clock. And I think this is probably one of the best ways that we can look at pitch class integers and show relationships. And in fact, show symmetry, how certain notes can map on to other notes or other sets. And so often we'll look at the clock to kind of show how pitch class sets, and eventually normal order and prime form and set classes, how they relate to one each other or how they're equivalent. Okay, so this is a really good way for us to look at how things are laid out in terms of our pitch classes. And so let me just talk about a few other things. So in tonal theory, we usually group our notes into, oh my gosh, that's a terrible trouble. Here we go. We usually group our notes into what we call triads, right? And we have this nice label. And oh, that's an E minor triad based on its interval qualities, right? And tertian harmony sort of is predicated on this idea of we have to have thirds. In order to have harmonies, we have to have thirds. And that's sort of the basis of our harmonies in tonal realm, right? So we're going to kind of get rid of that idea. There's a couple of ways that we look at this. Yeah, the first way we look at it is, hey, this is a triad, meaning this is a group of 3 notes stacked in thirds. Right? The other way we look at this is a minor chord, right? And that's the quality of it. And then we can be even more specific and say, this minor triad is based on E. And so we described it from a very general sense to a less general sense to being really more specific. And then we can even go a step further and say this E minor chord in the key of whatever is let's say it's a 1 chord in that key. So we can be really, really specific about how chords are organized and how where chords belong in terms of the larger tonal picture. Okay, so here's the other idea. We can take that same chord, right? And so this is still an E minor harmony. And those notes spread out at whatever distance, we could also go these notes here, right? If we take those 3 notes, we can say, well, that's a triad. It's a minor triad. It's an E minor triad, da-da-da-da-da-da. So we have a way of capturing a set of notes and describing it in a more compact form, right? And so we're going to do the same thing for pitch class sets, right? So let's take a series of notes. We might have an atonal theory. Actually, I'm just going to use the same set of notes. So let's take those notes from our E minor harmony again, and we're going to capture them using what we call pitch class sets. So pitch classes, remember, are the integers that we use, right? Specific notes. And pitch class sets are where we're going to take those notes and put them and group them together so we can organize them, manipulate them, and find relationships or similar pitch class sets across a piece. So instead of describing this as an E minor triad, we want to take our pitch class integers. And remember, this will take you a little bit, but this is pitch class 4. E is pitch class 4, 0, 1, 2, 3, 4. G is 7, and B is 11. And so we would say this pitch class set is 4, 7, 11. And so now instead of saying hey, this is an E minor triad, we're instead going to group these integers together like this. And we'll use commas, we'll use brackets, depending on the form that it's in. And we can describe it in its raw form, as you can see right now, which we would call a pitch class set. We can describe it where we order it in its most compact form, which is normal order. And then we can also organize it into what we call its prime form, where we're boiling it just down to its essential elements or its intervals, right? And so that's kind of the same as we do now, where we can just see the notes. We can see the notes as an E minor triad. in, you know, whatever inversion it's in, right? That's its most compact form. Or we can just say this is a minor triad, which is just telling us about its interval structure, right? So more specific to more general. Okay, so then let's race on back here. We have about 8 minutes left here. Pitch classes are grouped into what we call pitch class sets, right? Which I just described to you as how we group those notes together. So instead of calling it an E minor triad, we're going to say, hey, this pitch class set is 4, 7, 11, right? And so I just described to you kind of what we do in tonal harmony and then what we do in theory. And here's the analogy here, right? So in tonal music, we have notes, right? And then we can group those notes into harmonies, right? Like an E minor harmony. And then we can take those notes and put them in their most compact form to show how they sound, like in an inversion, right? In the most compact form of that, how is this chord sounding, right? And then we can say, well, in a general sense, that's a major minor 7. That's really just describing its intervals. So pitch classes can be grouped into pitch class sets, I'm going to abbreviate, which then can be put into a more compact form called normal order, which then can be boiled down just to its essential intervals, which we call prime form. And those prime forms can be organized into what we call set classes. And so that's sort of the organization that we're going to use here. And that's thinking a little ahead, but it's so you have this in mind and you see the direct analogy. So we have notes in a tonal realm. We can organize those notes to become harmonies. We can put those harmonies in their most compact form to describe how they sound. And then we can boil those harmonies down in their most compact form to what their essential intervals are, and we can call them, we can give generic names to those like we give to qualities of chords across the realm of tonal harmony. All right. Okay, so just a couple more things before we depart, and I wanted to point this out before you had to jump into some of the exercises that you have to do. And of course, this is being recorded, and I will post it on Blackboard so that if you missed anything, if you didn't get something, you can go back and check it. And of course, I'm happy to meet with anybody during office hours. No one's taking advantage of that, which I understand. But if you need to meet, I'm happy to meet. Okay, so let's take a pitch class set, right? We have down here. We can transpose pitch class sets through the operation Tn. And T really stands for transposition. And we could do this with harmonies, right? So if we had a harmony C major, we can transpose it up a major third, and it becomes an E major harmony, right? And so if we were describing that in terms of set class theory, here's my C major chord. We went, oh, let's transpose this up to E major, right? It's the same essential intervals, it's the same structure, right? We've moved it up a major third, yes? How would we describe that in terms of set theory? Major third. Well, remember, we don't do qualities anymore. We're just working with integers. So how many half steps is that? 1, 2, 3, 4. So we've transposed this. I'm going to use the letter I, interval 4, meaning 4 half steps. We've transposed this by 4, up, right? And when we're describing our intervals, they're always going to work up, and I'll describe that later. So we would say T, we perform the operation T4 to this triad. We transposed it up 4 half steps. Notice the index number is describing the half step distance between the 2 harmonies, or in this case, the 2 pitch class sets, right? If we're talking in set class or in set theory. So Tn describes transposition. The number n, the index number, n is the index number, describes how many half steps to transpose the set. The operation is just simple addition in this case. So if we have T2 here, we're just saying, hey, let's transpose these pitch class integers, 4, which is E, 5, which is F, 11, which is B, up to half steps. So all we have to do is plus 2, plus 2, plus 2, and we get to where we're going. Okay, so one more important thing that I have to describe to you that I kind of glossed over before we get into this. Let's go back to our clock real quick, and I only have a few minutes here. And so I'll make another video about transposition and mod 12. So when we get to transposition, what's going to happen? If we have the pitch class set 4, 5, 11, like you just had, and you transpose it plus 2, plus 2, plus 2, what happens? 6, 7, 13? Well, we can't use 13, right? Because 13 is not within our mod 12, our 0 to 11 mod 12. And that's a little bit of a mind twist, because when I say mod 12, you go, where's number 12? But remember, 0 is one of our numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to 11. So we're actually counting 0 as one of our numbers in mod 12. So if we have to stay in this realm of 0 to 11, how do we figure out what 13 is? Well, if we have 11 right here and we add 2, we're going 11, 0, 1, right? Or we're going 11, which is B, and we transpose it up to C, 0, 1, D sharp. Or excuse me, C sharp, C sharp. So really, when we say 11 plus 2, really we mean 1. Yes? So the way to get any number, let's say we're dealing with 13, back into mod 12, is we have to subtract 12 from it, and we're back in mod 12. Or if we have a negative number for some reason, let's say we have a negative 6, we add 12 to get back into mod 12. 6. Or if we have a really large number, let's say somehow we have a Tn operation that has T10 or T12 or something like that. Say we have the number 26. We need to get back into mod 12. We subtract 12, however many times it takes to get back into our mod 12 range. Yes? So remember, our pitch classes have to be in that 0 to 11 range. And so we're constantly having to, when we're doing these addition and subtraction operations, we are constantly having to take numbers and subtract 12 or add 12 to get back into our 0 to 11 realm. Okay, so if we go back really quick, and we're about out of time here. If we go back really quick and look at this, you can see that if we transpose this by 2, 4 becomes 6, or F sharp. 5, which is F, transposed up 2, becomes 7. And 11, transposed up 2, is 13, but if we put that back into mod 12, it's really 1. And I think this is where the clock comes in handy, because if we're doing T2 to all of these, 4 becomes, like I said, 4 becomes, oops. One, 2 becomes 6. 5, 1, 2 becomes 7. And 11, 1, 2 becomes 1. So this idea of mod 12 is a little bit tricky to understand. But I think if you use the clock face, it really helps to show where you are. Yeah? Any questions before we take off? I'll use this video as kind of as a starting point, and I'll make just one or two more on transposition and basic mod 12 transposition and inversion of pitch class sets. But I wanted to give you this intro because it's a little bit of a difficult thing to understand at first. So any initial questions about that? Get as many modes of learning as possible. So if you can read, watch the videos, do some exercises and your self-tests to kind of to figure out what's going on here, all the better. And of course, I'm happy to spend time with you as well during office hours or any, if you need to plan outside of that, that works too. Okay. Good. So graded assignment due for Friday, finishing up chapter 26. And then we'll start to chapter 27. All right. Stay healthy. Stay sane. Get some exercise. I'll talk to you guys next week. In the meantime, please reach out if you have any questions. All right. Ciao. See you guys. Be well.